This is the first section in the differentiation chapter, 9.1, differentiating sine and cos. So you need to know what sine and cos become when you differentiate them. And also you need to be able to prove them from first principles. So the first thing is, let me give you what the differentiation of them are. So if y equals sine x, then dy dx is cos x, and if y is cos x, then dy dx is negative sine x. So you do need to know these are not in the formula book. Now sometimes you need to differentiate something where let's say it's sine of something x. Let's say you needed to differentiate sine 3x, for example. So not just x, but something x. Then dy dx becomes this k cos kx. Now this is what we call the chain rule. We'll talk more about this later on and look at really quick ways to remember this. But if we had y equals something x, y equals cos something x, then dy dx in this case would be negative k sine x, sine kx. So do you notice that the number that's here appears at the front there, and this kx part doesn't change? It's the same with the bottom one. The k appears at the front there, but this kx part doesn't change. And going back to the first principles differentiation, proving something from first principles. So just as a reminder, what you are trying to prove, that f dash of x equals the limit as h tends to 0 of f of x plus h minus f of x over h. And sometimes there's some extra information they give you, but these small angle approximations are useful in proving something from first principles, and there may be one or two other bits of information they may give you, and we'll look at those in a minute. But the another important thing is when you differentiate sine and cos, then you're always going to be working in radians, okay, because we're using this small angle approximation actually to prove these, and this only applies when we're dealing in radians. So it's asking us here to prove that when we differentiate sine x we get cos x, and it's given us a couple of bits of information here. It says that you may assume that as h tends to 0, that sine of h over h tends to 1, and sine of cos h minus 1 over h tends to 0. Now why is that? Let's have a look at why these statements are true, rather than just saying, okay, I'm just going to accept they're true. Why are they? Right, let's have a look at the small angle approximation. So if I've got sine x, let's write this as sine x over x. Well, as x tends to 0, then that means that this becomes small. We can use the small angle approximation. So as x tends to 0, this is approximately x over x. Yeah, so this is the small angle approximation, and that is 1. So that's why sine h over h, as h tends to 0, tends to 1. So how about the cos x ones, or the cos h? So if I had cos x minus 1 over x, okay, so what happens as x tends to 0? Well, as x tends to 0, I can use the small angle approximation for cos x, and that's going to be 1 minus half x squared. Okay, so this bit here is the small angle approximation, minus 1 over x. Now, what does that equal? Well, what happens at the top is you got 1 minus 1, so you'll have negative half x squared over x, which just becomes negative half x. So as x tends to 0, basically that's going to tend to 0. So as x tends to 0, then actually this statement here will tend to 0, won't it? So that's why we can use these statements here. They're basically using the small angle approximation as h tends to 0. Right, so let's do the proof to show that sine x, when it's differentiated, becomes cos x. So the first thing is we want to use the function notation. So f of x we're going to let equal sine x, and we want to prove the derivative, and the derivative is the limit as h tends to 0, and remember it's f x plus h minus f of x over h. So now we can replace that with actual sine, so that becomes sine x plus h minus sine x over h. Now this bit here we're going to use the double, not the double angle, it's not a double angle, we're going to use the addition formula. Do you remember cos A plus B? Yeah, okay, so we're going to do that. So this will become at the top, so sine A plus B is like sine x cos h plus cos x sine h, so that's just a double angle, minus sine x all over h. From there we're going to factorize the top. Now there are two terms that have got sine x in, so I'm going to put sine x outside of brackets, which means in the brackets I can put cos h minus 1 plus cos x sine h all over h. Now, do you recognize this bit and this bit? Do you recognize them from up here? Yeah, so they're going to come into play in a moment. Now everything here is over the same denominator, so actually what you could do is you could say, right, you've basically got sine x cos h minus 1 all over h plus the second bit all over h. Let's actually write that down. So we've got equals sine x cos h minus 1 over h plus cos x sine h all over h. So we have these bits here. You see that? Can you see this? Basically, that's what we've got at the top. So we can use the rules that they've given us, and we can say, right, okay, this bit here will tend to 0 as h tends to 1, and this bit here will tend to 1. So what we're left with, as h tends to 0, you basically got sine x times by 0 plus cos x times by 1. And what does that equal? That just equals cos x. So there we go. We've proved that when you differentiate sine x, you get cos x. And I suppose we'd finish off by saying, therefore, since f dash of x, or f of x equals sine x, s dash of x equals cos x. So you may be asked to reproduce this in exam and prove either sine x or cos x from first principles. So nice easy ones here. So we're going to use these rules up here where we have k. So a, if you differentiate that, you'll have 2 cos 2x. So notice the bit after the sine, this bit here doesn't change. But it's almost like that bit differentiated, isn't it? 2x differentiated is 2. B, this will become negative 5 sine 5x. So again, that bit doesn't disappear, but it's like we're looking for that k. And then C, we've got 2 terms there. So I suppose really I should be writing dy dx equals dy dx equals, rather than just writing down something floating around in the air. So let's put b dy dx equals, and we'll do it properly here. So dy dx equals, so this will become, so we've got a constant here. So basically that it's going to be 3 lots of whatever cos x is differentiating. That's negative sine x. Then we've got another constant here, but when you differentiate it, you're going to end up with 4, aren't you? 4 cos 4x. So actually you end up with 8. So this is like the 2 times the 4 there. So you end up with 8 cos 4x. First thing, finding stationary points. Now what do we know about stationary points? Dy dx equals 0 at a stationary point. So first thing we want to do is to differentiate this expression we have. So that will give you half x differentiate is half, and then cos 2x differentiated will become negative sine, or negative 2 sine 2x. So that's just what this bit becomes. There's a negative there already, so it becomes plus 2 sine 2x at the stationary point. So at dy dx equals 0, we'll have basically half plus 2 sine 2x equals 0. So we want to rearrange this so that we can solve it. So that's going to give us 2 sine 2x equals minus a half. Divide both sides by 2, we have sine 2x equals negative a quarter. Let's find the principal solution by doing the sine inverse of negative a quarter. So let's do that. And remember, we are in radians. Sine inverse negative a quarter. And to 3 significant figures, it's negative 0.253. 253. Okay, so that's my principal solution. Now let's use a cast diagram to work out if there are any other solutions. And then once we've done that, then we'll divide them all by 2. So we've got CAST 0, and we're going to go around twice because we've got 2x. That means go around the cast diagram twice. Pi over 2, pi, 3 pi over 2. So our principal solution is negative 2.53, which is going to be here. So that's a gap of 0.253 there. Let's finish off the cross. We've landed in the part of the cast diagram where sign is negative. Where else is sign negative? It's negative over here. So we are interested in this part of the cast diagram and this part of the cast diagram. So that's going to be, let's get the right color, green. That's also 0.253. So let's write down what all our values of 2x are. So we have our principal solution of negative 0.253. We also have pi plus 0.253. We also have 2 pi minus 0.253. We also have 3 pi plus 0.253, and we also have 4 pi minus 0.253. So now what we're going to do is divide those all by 2, and then we'll reject any solutions that are not in this range between 0 and pi. So 0.253, negative 0.253 divided by 2 gives us negative 0.127. Next solution, so we've got pi plus 0.253, divide that by 2, 1.69, that's 1.70 basically, 0.70. So we've done that one, we've done that one. Next one is going to be 2 pi minus 0.253. We'll divide that by 2. We're still underneath pi, 3.02. The next one is 3 pi, and we want to add on 0.253. We'll divide that by 2. That's well over pi, so this one was fine. Reject this. That one's definitely going to be over pi as well. So the only two values which we can use are going to be these two. We reject that one, it's not in a range. Now it does ask for the stationary points, which means coordinates. So we found the x coordinate of the stationary points. We now need to find the y coordinates by substituting these values of x into the original equation. So if I substitute in the 1.70, that gives me 1.82. And if I now just scroll back and change that 1.70, delete it and change it to 3.02 in both places, 3.02, that now gives me a y coordinate of 0.5394, so 3 significant figures are 0.540, so 0.540. Now I've done a lot of rounding here. It probably would have been best if I had used the exact value here, and then use the answer button. That would be better, but you'll get some leeway when you do this in the exam. So stationary points are, I'm going to write them as coordinates, 1.70, 1.82 and 3.02, 0.540. Right, you can now do exercise 9A on pages 2, 3, 4. Oh, it's only just page 2, 3, 4. So let's scrub that out. Just page 2, 3, 4.